The results that you can get after scanning your infrastructure with an automated vulnerability management tool like Nessus or OpenVAS can depend on a lot of factors, because no two environments are the same, no two scanning tools are the same, and, well, no two admins who configure those tools are the same. But we do have some things in common, so let's have a look over those. So first of all, in order for a vulnerability scanner to work properly and to produce some useful information like actual vulnerabilities, it needs to know what to look for. So a vulnerability scanner, it's only going to be as good as its vulnerability database. Some tools get this information dynamically from downloadable databases or plugins. Others just have a built-in predefined database. But this is where the value of a paid subscription comes into play. Most commercial products out there are going to have a much better and up-to-date vulnerability database. Although you should be aware of the fact that some smaller security vendors out there simply repackage existing open source information and then resell it to you back as proprietary information. So to better talk about the results of a vulnerability scan, we should introduce something called the Security Content Automation Protocol, pronounced SCAP or SCAP. And this is a method for standardizing and automating the vulnerability management and policy compliance in your organization, which means that SCAP is a protocol that can be used by a vulnerability scanner to automatically determine if a host meets some configuration baseline. So we can use it to answer things like, does the host pass the necessary test? Is that host secure enough for us? MITRE is the one that actually developed a lot of the SCAP components, and the protocol actually defines a number of open standards that are used to enumerate software flaws and configuration issues related to security. And as we just said, compatible scanners can use SCAP to determine if a host meets some predefined configuration baseline. Now, in order to do so, it defines some identifiers that help us describe specific platforms or vulnerabilities. Now, some of these identifiers are as follows. The first one is called CVE, or Common Vulnerabilities and Exposure, and the official website is at mitre.org. And you've probably seen notations like these before, so if we just search here for a specific vulnerability, like one that applies to Apple iOS, let's say, and select the first one. All right. Now, each vulnerability actually looks something like this. Starts with the CVE keyword, followed by the year when it was discovered, and a unique index. Of course, it's going to provide you with a lot of more information here, like a description, URLs for reference, any dates or milestones that are relevant for this specific vulnerability. Another one is called CPE, or Common Platform Enumeration. If we visit the website right here, it's basically a way to describe the platforms to which the vulnerabilities apply to. So this type of notation, or this standard, actually describes operating systems, applications, hardware devices, chipsets, anything that can have a vulnerability and is considered to be a platform. And this database is actually used every time Nmap or other network scanning tools, whenever they try to identify the operating systems that are running on a specific scanned host. If you look for some CPE examples, you're going to find that the strings that describe a CPE kind of looks like a URI. And if you look under Wikipedia here, which has some nice examples, and you scroll down, you're going to see a couple of examples here at the bottom for Microsoft Windows or Microsoft Internet Explorer. And basically the strings here are going to describe things like the vendor, like Microsoft in our case here, the product, the version, any updates or additions that might be relevant, up to the language or any other additional details that we might add at the end of the string, just to uniquely identify a specific version of a software or of a hardware platform. Another one is CCE, which is under the configuration section here, and it actually stands for Common Configuration Enumeration. It's basically just a collection of best practices for configuring hardware and software. Another indicator is the CWE, that is Common Weakness enumeration, which is just a collection of flaws in the design of software that could potentially lead to vulnerabilities. So for example, if we were to look under, let's say, business logic errors here on the left, and one of them being the authentication bypass using an alternative path. Right? You're going to find a lot of description here about how this is going to be a relevant weakness in your software and how you can also mitigate it. And lower on the same page here, if you scroll down, you're going to find a list of observed examples. So these are instances where this specific type of weakness has been observed in real life as a vulnerability. And yet another indicator is CAPEC, that is Common Attack Pattern Enumeration and Classification. That's a mouthful. It's basically very similar to the attack framework or the attack database that we've seen in a previous episode, but this one actually focuses on the application and the exploit, while the attack framework focuses more on the attacker and the intrusion event. And just like with the attack framework, you can also find a list of observed methods and attack patterns. For example, abuse existing functionality. All right, this is where we're going to find things like flooding or resource leak or functionality misuse vulnerabilities. Don't go just yet, we have a couple more. One of them is OVAL. This is Open Vulnerability and Assessment Language. This is mainly used for reporting because it describes using XML the state of a system from a security perspective. So basically just a security assessment report. And finally, the last one is XCCDF. That's Extensible Configuration Checklist Description format. Again, we're using XML here, and it's used to develop and to audit security checklists. So you're basically making security checklists that you run and you check in your environment for configuration best practices. Now, as you know by now, a vulnerability scan is going to generate a report of all the vulnerabilities found in a system or in a network, just like we've seen in the previous video with OpenVAS. Now, most reports generated by these tools are going to be pretty straightforward, and they are basically going to just list the assets, their vulnerabilities, and then a CVSS score attached to them, because that score is going to be very useful to you to determine how critical that specific vulnerability really is. So CVSS, which stands for Common Vulnerability Scoring System, is a unified metric, and this score, this metric, takes into consideration multiple factors, and we're going to cover these in more detail in a moment. But they're going to help you tremendously when you need to prioritize what exactly you need to fix. So where do you need to focus your efforts first? Now, careful when prioritizing, because normally the highest CVSS metric is going to tell you that that is the most critical vulnerability in your system, but that might not be the single best factor. And keep this in mind for the exam as well, because they're most likely going to ask you about this. Sometimes a medium or a low vulnerability that can be fixed in 1 or 2 minutes or 5 minutes might take precedence in front of a critical one that you can only fix in 1 or 2 weeks. Now, vulnerability scanners are going to make mistakes from time to time. Not because they're people too, but because they might not have enough reachability. For example, you might have some network filtering in place that simply doesn't allow the scanner to reach the device it's supposed to scan. Or it reaches that device and it doesn't have enough privileges to interrogate those services or interrogate or read those configurations in there to provide you with an actionable report. The ideal situation for a vulnerability scan is called a true positive. That means that a vulnerability that matches a CVE is really present on that host, on that device, on that piece of software. It's really there, no doubt about it, it's true. Another acceptable result is a true negative, which means that no vulnerability has been detected and no vulnerability theoretically exists on that host. That's also okay. Careful with this one. You can only scan for things that you already know about in your database. So if a vulnerability is not detected, it simply means that it is not in your database. The vulnerability might be there, it just hasn't been discovered by anyone yet. But vulnerability scanners can also provide false results. It's true, and you have to take this into consideration because they take a lot of time to investigate. Now, the bad results are false negatives, when the scanner fails to detect a vulnerability but tells you that everything is okay. And false positives when a scanner alerts you about a vulnerability that doesn't really exist. Now, this is not exactly so dangerous from a security perspective, but it's going to be time consuming, right? You have to investigate to see if that vulnerability actually applies to you, if the piece of software that was detected by the scanner is actually in there and it has the right version for that vulnerability. It's not going to be a concern from a security perspective, but it's going to be time consuming, and you could better spend that time fixing, true positives. All right, so what can you do to avoid these errors as much as possible? First of all, very important, make sure all your hosts are up, all your scanning targets are up and running. Validate the resulting inventory. Is everything that you would expect in there? And make sure your scanning traffic doesn't get blocked or dropped by any firewall policies. Then think about credentialed and non-credentialed scanning. Expect non-credentialed scans to produce much more false positives, and this is also a very important topic for the exam as well. They simply produce more false positives because they don't have as much visibility as credential scans. You might need to reconfigure or fine-tune your scanner if the number of false positives is too high. And also, fine-tuning might be required to help your scanner learn what is a false positive and what is a false negative, especially if the incidence of either of them is very high. Check your baseline. If your scanner uses some pre-configured baseline and does some heuristic analysis, it might trigger an alert from any valid change that actually happened in your network. Also, remember to fine-tune your scanner to only look for things that apply to you and to your environment. There's no point in scanning for operating systems and services that are not present in your environment at any point in time. And keep in mind that your vulnerability scan might return results about vulnerabilities that are extremely difficult to exploit. Things like vulnerabilities that require physical access or admin privileges. Now, are these going to be a cause for concern? Well, yes, probably, but they might not be of the highest priority, simply because it's so difficult to have everything in place in order for that successful exploit to happen. So generally, trust but verify. Double check the scanner's results every single time. Make sure that at least everything that you expect to find is in there. Okay, so coming back here to CVSS, which we just discussed a couple of moments ago. So a CVSS score is an overall numerical value that is assigned to a specific vulnerability. It's a way of saying how bad do you expect a vulnerability to be, how critical is that vulnerability. It helps you tremendously with prioritization, because just by looking at those higher CVSS scores, you might decide that those are worth fixing first, because those are critical vulnerabilities that can damage you the most. One more thing here, don't confuse the CVSS, which is a score, with CVE, which stands for Common Vulnerabilities and Exposures. CVE is simply a list, a database of all the published vulnerabilities, all the vulnerabilities that we know about up until this point. And of course, this list is going to include a CVE ID, a description, any relevant dates and comments about that vulnerability, but the CVSS score is not going to be reported in the CVE listing. So if we were to explore the CVE database and just search for some vulnerabilities about ASUS routers, and let's just select one of them here in the list, I'm going to see that this entire page here doesn't have any mention of a CVSS score. So just by looking at this page, we cannot simply deduce how critical this vulnerability really is. To find out the real score, we need to head over to the NVD, or the National Vulnerability Database. This is where we can search for a specific CVE, and we're going to search for one of those ASUS vulnerabilities that we've just seen in a previous page. And this time, if we click on the vulnerability ID, we're going to be able to see a score and a vector. Right? We can see that this is a high vulnerability based on the score right here. And in just a couple of moments, we're going to understand more about how this score is calculated and what this ugly vector string on the right here actually means. All right, so let's dig into an example of a CVE. Now, if you've ever seen some news about vulnerabilities in the online press, then you've probably seen something that kind of looks like this. This is just a code to identify a specific vulnerability in a specific year. Now, the score, on the other hand, the CVSS score or metric, this is an indicator of how severe a vulnerability is considered to be. Now, this should help you with prioritization, but it should not be the only factor when you decide which issue to address first. Try to also think about your own experience and what you know about your environment and how likely is a specific vulnerability to manifest, to happen in your environment. The CVSS score thresholds are also one of the favorite exam topics of CompTIA CySA Plus, and you should remember them. Of course, the 0 score means that there is no vulnerability. You're going to have low vulnerabilities between 0.1 and 3.9. Everything up to 6.9 is going to be considered medium, just like the 6.1 we can see here on the screen. Between 7 and 8.9, it's going to be high, and finally the last integer here between 9 and 10, those are going to be considered critical vulnerabilities. Try to remember this for the exam. One way I kind of try to remember this list is by thinking about the fact that critical includes one single integer between 9 and 10, high includes 2 between 7 and 9, medium has a range of 3, and low has the final range of 4, right? Try to remember them this way if it helps you in any way. And finally, we also have this weird looking vector string at the bottom of the slide here, which is just a description of how did we get to that 6.1 score. So let's see what those symbols actually mean in the CVE vector, where the highlighted parts are actually shorthand notations for some parameters that help us characterize that specific CVE. So for example, the attack vector, the attack or access complexity, how many privileges are required to conduct an exploit, how much user interaction is required, what is the scope of that vulnerability, and also how is the CIA triad affected, that is confidentiality, integrity, and availability. So let's see what these metrics actually mean. Now, according to the standard, the CVSS score is actually calculated from a number of metrics. And in most cases, it's calculated just from the base and the temporal metrics. Now, the temporal metrics and the environmental metrics are considered optional because the temporal metric measures the current state of the exploit technique, or how available is the exploit code right now. Also, the existence of any patches or workarounds, or the confidence in the description of a vulnerability. And it's called a temporal metric because anything we measure from these points of view can change from one day to the next, or from this year to the next one. On the other hand, environmental metrics are also considered to be optional because they are relevant from a fine-tuning perspective depending on a specific user's environment. So for a specific environment, a certain vulnerability might have an increased environmental metric simply because that environment is by definition, or by its current configuration state, more vulnerable to that kind of attack or a kind of exploit. And one thing to keep in mind before starting to talk about the base metrics is to assume that the attacker has already advanced knowledge of the system and of the weaknesses inside of that system, including general defense mechanisms like firewalls, rate limitation, traffic policies, and stuff like that. So assume that the attacker already has knowledge about your system, and let's see how exactly we can calculate that base metric to describe a vulnerability. So we have a number of CVSS base metrics, and the first types are going to be called exploitability metrics. The first one is called the attack vector. And this is a metric that reflects the context necessary for the exploitation to become possible. In other words, where should the attacker be located for the exploit to succeed? And of course, this metric value is going to have a larger score the more remote the attacker can be, because we can safely assume that the potential number of attackers that can exploit a vulnerability across the network is going to be much larger than the potential number of attackers that can exploit a vulnerability that requires physical access and physical presence next to the device. So the worst metric value in this situation would be N, which stands for network, and it means that the attack can be conducted from across multiple networks, even across the internet. And this is what we normally call a remotely exploitable vulnerability. The next one, which is a bit better, is adjacent, which means that the attacker is supposed to be located onto the same network or the same subnet or VLAN as the target. An example of an adjacently exploitable vulnerability is also one that can be exploited over a securely administered VPN, for example. Local assumes that the attacker has some read, write, or execute permissions on the target device, which can be performed also over an SSH connection, for example. And it also includes the situation where the attacker relies on user interaction of some other person to perform those actions required to exploit the vulnerability, for example, using social engineering techniques. And finally, the physical attack vector means that the attacker is required to physically be in the vicinity or to touch or manipulate the vulnerable component. Now, the attack complexity is going to include all those conditions that are somehow outside of the attacker's control, some conditions that the attacker must overcome in order to be able to successfully deploy its attack. Now, most situations, these conditions are going to be mitigated by the attacker trying to gather more information about the environment and become better prepared to launch the attack. Of course, a low attack complexity is going to mean that these special circumstances don't exist at all, so the attacker can expect success every time he or she attempts to exploit that system. But on the other hand, a high attack complexity can mean any number of things beyond the attacker's control. So for example, situations where the attacker must obtain some specific files, maybe some hashed passwords, maybe some shared secrets, or situations where the attacker must prepare the environment beforehand, like making sure that it's going to win a race condition or inject some malicious code in order to run the exploit. Or even situations where the attacker must inject themselves into the logical network path between the attacker and the target to intercept and perhaps even change the network traffic that goes through that segment, which is basically the definition for a man-in-the-middle attack. Next up, we have the privileges that an attacker must have before successfully attempting to exploit that vulnerability. The base score, of course, is the highest if no privileges are required, which means that anybody can actually exploit that vulnerability with no privileges whatsoever. But of course, we're going to have these values of none, so the attacker is going to be unauthorized prior to the attack and doesn't require any access to the system, to its settings. A low metric here is going to mean that the attacker requires some privileges, but perhaps the privileges of a basic user, a non-privileged user. A high privileges required metric means that the attacker requires privileges that provide administrative or root level control over the system in order to conduct its exploit. User interaction describes the requirement for some other human, other person, other than the attacker, to interact and to participate in the successful compromise of that vulnerable component. Well, of course, the metrics of none are going to describe the fact that the system can be exploited without any interaction from any user, while a metric of required means that the successful exploitation requires some user to take some action before that vulnerability can be exploited. One example here would be the requirement for a user to double-click a file or to install a piece of software on their machine or to click a link that redirects them to a specific web location. The scope metric describes whether a vulnerability in one component can impact other resources outside that component's security scope. Well, what is the security scope? Let's assume that I have a web application that is the sole user of a database. So the database is only being accessed by that web application. This means that the database belongs to that web application's security scope. So if I compromise the web application and then I am able to access or compromise the database as well, this means that the security scope is unchanged. It's still the same one. But on the other hand, if I compromise the web application and that compromise allows me to pivot and then compromise, let's say, the employee workstations in the same company, well, that is going to be a change of scope. Finally, the impact metrics are going to reflect the impact to confidentiality, integrity, and availability, strictly speaking about the affected target. And of course, we're going to have some metrics here, such as high, where let's assume that there's going to be a complete loss of confidentiality, which results in all the resources being divulged to the attacker, so the attacker gains access to all our data. A low impact is going to assume some loss of confidentiality, so perhaps we're not disclosing very sensitive information, or the attacker doesn't really have any control over what information is obtained. And of course, none is for when there is no loss of confidentiality, integrity, or availability in our network. When it comes to availability, a high metric here is going to mean a total loss of availability, so we cannot use those resources anymore. That's going to be the result of a distributed denial of service, for example. A low metric is going to happen when performance is just reduced or there are interruptions in resource availability. Then we reach the temporal metrics, and the first one here is going to be exploit code maturity. Now, this is going to measure the maturity of the exploit code, but based on the current state of the exploit techniques out there. So how available is the exploit code? Has it been defined? Is it readily available for everyone to use? Or is it just some type of proof of concept? Now, the metrics here are going to start with not defined, of course, which means that there is insufficient information to actually determine if there is an exploit or not. We can never be 100% sure that there is no exploit code out there, followed by a high metric, which means that there is a readily available code out there that can be used to exploit that vulnerability. Or even worse, I would say, no exploit code is actually required at all. So the vulnerability can be exploited without any custom code, just by using perhaps some crafted commands or a specific sequence of tasks. Now, the details that actually make this a high metric is the assumption that the exploit code is going to work in every situation, or can be even delivered in an automated manner by a self-propagating worm, for example. Now, the next level is functional, which is very similar to high, because we also have a functional exploit code readily available, but we don't have the quote-unquote benefit of automation and the assurance that the exploit code is going to work in every situation. A proof of concept metric basically means that there is some exploit code available, but as a proof of concept. So an attack demonstration can be conducted, but it might not be practical, feasible for most systems out there. So the code or the technique exists, but it might not be functional in every situation. And of course, the last one is unproven, or no exploit code is available, or an exploit is just theoretical. The next one is remediation level, which is a very important factor when it comes to prioritization, and it basically tells you whether there is a solution out there for that weakness, for that vulnerability. And we're going to have some metrics here as well, starting with not defined, which means that there is insufficient information to actually determine if there is or isn't a fix or a patch out there, followed by unavailable, which states that there is no solution available, or it is impossible to create one or to apply such a solution to this vulnerability. W for a workaround means that there is an unofficial or a non-vendor supported solution out there, probably developed by the community or by somebody who has created the patch on their own, but it's not going to be supported by the vendor itself. A temporary fix, abbreviated as a T, is an official but a temporary fix available. Basically, this is going to be temporary simply because it most likely relies on disabling some other necessary functionality in order for the fix to work, or making some unwanted changes to your system. And of course, the last one and the best one actually is going to be the official fix, where there is an official patch or an update or a service pack published by the vendor that fixes that specific vulnerability. Now, for remediation level, you can probably see why this is going to be a temporal metric, because when a vulnerability is first discovered, now its state is going to be unpatched. So as time goes by, workarounds, fixes, updates, and upgrades will be published that are going to fix that vulnerability. So depending on when we are in a specific point in time, this temporal metric here might range from an unavailable one to the official fix. Report confidence is an interesting one, because it's a metric that tries to describe how confident can we be that the vulnerability actually exists. It might be that we don't know exactly what is the root cause of the vulnerability so we can properly describe it, or that the vulnerability was identified by research or by code analysis tools, but nobody has been able to replicate it just yet. And the metrics here, of course, range from confirmed, where we have detailed reports and we can test for the existence of the vulnerability. We probably have some dedicated codes that can validate, or at least a command or two that can confirm that the vulnerability exists. The second one is reasonable, where we have some significant details, we have some published information, but we don't have full confidence in the root cause, or we don't have a code or a validated method to confirm the existence of that vulnerability. And of course, unknown, which means that there are reports of impacts that indicate the vulnerability might be present, but we don't know the cause of the vulnerability, or even the reports might not even be in sync as to what the vulnerability really is. And the last one, the security requirements, is actually an environmental metric because they're about fine-tuning. It's basically a way to allow the cybersecurity analysts to customize their own CVSS scores to reflect the importance of the affected IT asset to their own organization, measured, of course, in terms of CCNA. Now, if an asset, for example, supports a business function for which availability is the most important, well, then the analyst can assign a greater value to the availability relative to the confidentiality and integrity. Right, so it can shift the score just a bit into the favor of their own internal company requirements. Right, so now that we know what the attack vector actually means, let's go back to our initial example here of our CVE example, and we can see that the description actually says that it applies to Apple iOS, several versions here, and it says that processing maliciously crafted web content may lead to universal cross-site scripting. Right, so this is a vulnerability with a CVSS score of 6.1, which makes it a medium vulnerability, and the vector that we have here on the right. And if you hover over this vector, you're gonna be able to actually read how it was built. So starting with the attack vector, which is network, it can be conducted across the network or across multiple networks. An attack complexity of low, so not many resources, not much information is required to be conducted. No privileges are required. We don't need access to the target device in order to run this exploit code. User interaction is required, most likely due to the nature of the mobile device, which is the Apple iPhone. The scope is going to be changed, confidentiality impact is going to be low, integrity impact is going to be low, and no impact for availability. All right, so this is how you decode this vector, which explains how the metric was actually calculated. Now, there is one more thing that should be covered, because up to this point, we know what these parameters actually mean, but there's no way to connect those parameters to that base score. So how do you get from a change scoped to a score of 6.3, for example? Well, the explanation for this relies on the fact that there are certain equations which are published along with the CVSS scores that let us calculate those values. Now, the good news is that the equations behind these calculations are not necessary for you to know for the exam, but just in case you're curious, make sure you visit this link right here. I'm going to add it to the video description as well, just to figure out how that score, that final score, is actually obtained from your metrics. And I'm going to provide you with another link here, which is actually a CVSS score calculator, which allows you to pick and choose all these metrics here, and then it generates a score automatically for you. So for example, if we were to choose an attack vector of a network, a high attack complexity, low privileges, no user interaction, unchanged scope, no change in confidentiality, low impact in integrity, and high availability impact, I'm going to end up with a CVSS score of 3.1, which is not that high actually, and you also get the automatically generated vector string here at the bottom. Right, we can also add some more information here, of course, like the temporal score parameters and the environmental score parameters, just in case they apply to your specific environment. Alright, so for the exam, make sure you at least recognize all those identifiers defined by SCAP, understand the different types of results that can be provided by scanning software, and especially understand the difference between false positives and false negatives, and also make sure that you can navigate a CVE database and that you understand what is a CVSS score, how it is calculated, and what kind of information goes into that calculation. Alright, so thank you so much for watching. I hope this has been useful and informative. Don't forget to like and subscribe, and see you on the next episode.